In this video we're going to have a look at the standard model that represents fundamental particles, and the representation that's fairly common these days is this graphic here that shows all of those elementary particles. It's just a classification system for elementary particles. Now what we mean by elementary particles is the smallest building blocks of matter, and our understanding of what is an elementary particle it has developed over time, given that at one point in time it was believed that atoms were elementary, they couldn't be broken down into anything smaller, and then we eventually discovered that they consisted of protons, neutrons and electrons, and then eventually we found that protons and neutrons were actually composed of smaller things as well. So this term elementary, what we really mean there is that it can't be broken down into smaller parts. Now, as I said, at one point in time we did think that the atom was an elementary particle. So while we have arrived at this understanding of what makes up elementary particles, it is possible that somewhere along the line, somewhere in the future, that we might find that these particles are actually composed of smaller parts again. Now this model was actually developed through experimentation and theory. So some of the particles were theorized and hadn't been discovered, others had been discovered through experimentation. We've confirmed the existence of a lot of these particles. So for example, the bottom quark here was discovered in 1977, the top quark was discovered in 1995, the tau particle was discovered in 2001, and you may remember back in 2012 the Higgs boson was discovered as well. So it had been theorized to exist, and then finally with the Large Hadron Collider we're able to identify the evidence for the Higgs boson as well. The first thing to identify about this classification system is that it's basically broken up into two parts. So we can see the left hand side there are the fermions, and the right hand side are the bosons. Let's just quickly talk about what they are. First of all, you can think of fermions as being particles. So they are things that have mass, and we consider that they're sort of the way that we would normally consider a particle. Should also mention here though that fermions are not necessarily elementary. There are some fermions that are composite particles, so made up of some of these elementary particles, and all of the fermions have a property of half-integer spin. Now half-integer spin is not something that we need to worry about for this course, but just mentioning it there if you're wondering what actually a fermion is. And fermions consist of two types of particles. You can see there that they're broken up into the purple lot at the top there being quarks and the bottom being the leptons. So it consists of two subgroups of quarks and leptons. Now we'll have a look at quarks and leptons in more detail and identify what some of these particles actually are. The second grouping that I mentioned there is the bosons. Now bosons are a little bit tricky to get your mind around. They are often called exchange particles. Now you might sort of go, well, what's an exchange particle? What do you mean by that? It's basically that they mediate some of the fundamental forces of the universe, and more specifically they mediate three of the four fundamental forces of the universe. The one that they don't mediate is gravity. We'll talk a little bit more about the fundamental forces in a coming video, but I'll just mention now that that's what bosons are, so exchange particles that mediate three of the fundamental forces. So we'll come back to that particular idea in a later video. In order to make a little bit more sense of these particles though, we'll start looking at the leptons to begin with, because you'll notice there's one lepton in particular that we have seen before, being the electron. There's a little bit more to unpack about these leptons though, so we'll have a quick look at what make up the leptons first. So with this classification key, what I'm going to do is sort of tie all the particles together in a way. So we're going to start out just by identifying what the particles are, so the name of the particles, We then have associated antiparticles. So this is a table of sorts. We then also have neutrinos that are associated with those particles, and then antineutrinos as well. So quite a bit that's summarized in that table above that we just saw. So the first one that we'll deal with is the electron. The symbol that we use for the electron is E. So pretty straightforward. We've seen it before. One of the properties that we need to be aware of about the electron is that it has charge, and the charge that it contains is -1. There's another number that we need to use here as well. It's known as the lepton number. Basically the idea of a lepton number is just that it gives us something that we can use to consider in interactions of subatomic particles. And I guess if you think about it as sort of being similar to say atomic number or mass number, it's simply a number that we assign to sort of count or to indicate how many there are. So if you're looking at a lepton number of +1, then you're basically looking at something that is a lepton. So the antiparticle for an electron is known as an anti-electron or a positron. The symbol for an anti-electron is E with a bar over the top of it. So E by itself is an electron, E with a bar is the anti-electron, or otherwise known as a positron. Now when we're talking antiparticles, we're basically just saying they have the same properties as the particle except for one particular property. And when we're talking antiparticles here, what we mean is that for the electron it has a charge of -1, the anti-electron has a charge of +1. And because it has a charge of +1, it's not the same as a lepton, so it actually has a lepton number of -1. So antiparticle has a lepton number of -1 because it's the anti to the lepton itself. Now the neutrino, we've actually seen this one before when we looked at radioactive decay. The neutrino that we're dealing with here is the electron neutrino, and we use the symbol nu, the Greek letter nu, with a subscript e to indicate the electron neutrino. The electron antineutrino similarly uses nu e, but it's got the bar over the top to indicate it's the antiparticle. Now neutrinos don't have any charge associated with them. So you might look at that and say, well, how is an antineutrino, how is it opposite to a neutrino? In this case, it's not the charge that we're dealing with, it's other properties. I'm not going to bother talking about what those properties are, that's above the scope of what we need to cover here, but other than to say that there are other properties that vary between the neutrino and the antineutrino. The lepton number for a neutrino is +1, so it is a lepton, and for an antineutrino it's -1. So there's the first lepton. The second lepton that we need to look at is the muon, spelled M-U-O-N, and uses the symbol of mu, so that symbol that's similar to, well, the same as what we use for micro. It's it's sort of a U with a bit of a tail at the front of it, or a combination of an M and a U. Similarly to the electron, we have an antiparticle for the muon that is the anti-muon, so mu with a bar across the top of it. There is likewise a muon neutrino, so in this case it's nu with a subscript mu, and then we have a muon antineutrino as well, which again, same symbol as the neutrino, just with the bar across the top. Notice that I've put them in the same row as the corresponding antiparticle neutrino, antineutrino, so they have the same properties as the corresponding electron, anti-electron, electron neutrino, and electron antineutrino. The third of the leptons is the tau lepton, or tau particle, which uses the symbol of tau. The antiparticle is the anti-tau, so a tau with a bar across the top. We have a tau neutrino as well, and we have a tau antineutrino. And again, charge and lepton number are all the same. You might then look at that and say, well, hang on, what's going on in this case? How are these things different if they all have the same charge and the same lepton number? The way that they're different is as we move across to the right, we have increasing mass. So to put that into perspective, the mass of an electron is quite small. The mass of a muon is about 200 times greater, around, roughly speaking, about 200 times the size of an electron, and then the tau particle is about approximately just a little bit less than 3,500 times greater than the mass of the electron. So you can see there that electron being a small particle, then we get larger to a tau particle that's quite significantly bigger. That actually means that the tau is sort of about, it's in the same sort of range of masses as protons and neutrons, so fairly large in terms of the size compared to the electron. Important to note here too that in talking about the leptons, we've talked about electrons, muons, and taus. If you go back up to the this diagram that we have up here, you'll notice that they appear here, here, and here, and then the electron neutrino, muon neutrino, and tau neutrino. Note that each one of those has a corresponding antiparticle, so we only represent the particles here, but the antiparticles then match up with those, as I mentioned, having all of the same properties except for one of them, in the case of the leptons, for being the charge, and then neutrino and anti-neutrino, it's a different property again. So there's the leptons. We now need to, we'll go across now and have a look at, or I'll put it in another video, for the quarks.